Okay, so second part of the second course. So I erase everything. And in order to express, as I have said previously, this notion of absence of arbitrage opportunity using functional spaces, okay, and functional analysis, but we are going to introduce the functional spaces I want to deal with. It will be related to the notion of what we call contingent claims and the notion of replication and over-replication. So it will be at the beginning some definitions. In the video, you will see me more erasing the board than doing mathematics. Okay, so definition of a contingent claim and related spaces, in fact. Okay. It's the definition 5 in 2 parts. Small a. A contingent claim okay, I denote it by U at, okay, is simply a F capital T measurable random variable. Okay, it's just a name for something that is F capital T measurable. And in this case, we write, so U, that will be the actualized value of my contingent claim, and since U at is something that is F capital T measurable, it means that intuitively it lies at capital T. So when I want to discount, okay, I have to discount with respect to the final value of the non-risky asset. So what I will denote by U will be U at divided by S0 capital T at. Okay? Because intuitively this random variable being F capital T measurable is something that lies at capital T. Okay? So before to continue the definition here, two little remarks. I remind you that for F capital T, I have taken in this course the power set. Okay? So it means that for me here, to be F capital T measurable is just to be a vector. Okay? The vector with a number of components that is just, okay, the number of elements in omega. I have no real measurability condition here because for F capital T, I take the power set. Okay? So intuitively, U at will just be something like this. Okay? U at W1, U at W, the number of elements in the universe omega. Okay? So from a financial point of view, what is the meaning of this? In fact, what we call contingent claim is deeply related to, let's say, European style options. Okay? That are options that you can exercise only at the end, at capital T. Okay? So for example, for you at, I can take, why not this one? Okay, it's an example among an infinity of examples. I can take this one, that is something that is F capital T measurable because it depends on the final value of the first Ricky asset, okay? And do you remind what is this?
The payoff of the call option.
So I have the payoff of a call option of maturity capital T and strike K on the first risky asset. Okay? I can also take this one, and I will have a put option in this case, and I can also combine, okay, I can also have, for example, let's take this one, something like this. So 1 over capital T, the sum from K equal to 1 capital T, ST SK1 at minus K plus. Why not? What is this from a financial point of view? So I am in the same family of these ones, okay? So I have in fact it's a call option, okay? An ASEAN call option. In the sense that here, instead of having the final value, I have the average of the trajectory from 1 to capital T. Okay? Well, just to say what? To say that this very large definition will represent intuitively for us the payoff related to European type options. Here I have given 3 examples among a lot. Okay? I can combine, so here you have an example only with the first risky asset, but you can do the same with the other one. You can combine the asset together in order to have, okay, kind of baskets. Just to say that this is related to something that is not very far from European style option. That may be, okay, classical one, ASEAN one, okay. Yeah?
What's the last index on the last of the results?
Here?
Inside the U vector.
The number of elements. So, keep in mind that something I have said in the previous session. For me, okay, what is a random variable? It's something from omega into R. Okay? So it is a vector, because I have a finite number of elements in omega. So, it's a vector containing a number of components or a number of lines here that is exactly the number of elements in omega times cardinal of omega.
Okay.
Okay? Cardinal of omega. Yeah?
So, this is at the top.
Yeah.
F at maturity, big T.
Yeah.
Is the power set of the sample set.
Yeah. It's what I have reminded at the very beginning of the previous session, saying that at capital T I know everything.
But, inferior to big T, it's not the power.
No. No. Okay, it's not. At 0 I know that it's the trivial sigma algebra. At capital T it's the power set, and in between it depends. I have given to you an example in the case of the binomial tree where this kind of filtration look like, or may look like, okay? Yeah, together with me, previous session, okay? I have done the tree with the binomial dynamic, and I have tell you what are the filtration, what is exactly the filtration in this case. And you see that between 0 and capital T, in general, you don't have the trivial sigma algebra, nor the power sets, okay? So this little remark just to tell you that what I call a contingent claim, so from a mathematical point of view, just something that is F capital T measurable, and in my framework, just a vector, okay? from a financial point of view, something that will be related to the payoff of European type options. Okay? So typically, the notion of contingent claim, okay, won't be the good notion if I want to model, let's say, an American call option. Why? Why? Because here you have a single value at capital T, single random value at capital T. And you know that for European option, okay, an European option, it's characterized by its payoff, that is what happened at capital T if I exercise or not. Okay, so a single random value at capital T is sufficient to describe a European option. For an American option, you have the right to exercise at any time. So it means that at any time you have to precise what happened if you exercise or not. It means that the description of a European option can be summarized by a single random variable, while the description of an American option, okay, is through stochastic processes. What you need to describe what happened at any time, while for European option, it is sufficient to describe what happened at the end, because you have the right and not the obligation to exercise at capital T, not before. Okay? There we go. Contingent claim, this one. Okay. Second part of the definition. So I don't have colors as usual, so I will try to do my best because I have two definitions in one here. So, a contingent claim. Contingent claim. U at is replicable. So I will give the definition of what is to be replicable and also to be respectively over-replicable. So the resp in means respectively over-replicable. So a contingent claim U at is replicable or respectively over-replicable, okay? If there exists a self-financed portfolio I have to precise just. So a contingent claim U at is replicable. I have missed something in my definition here. I had it here. Replicable at price small a. Okay, replicable or over-replicable at a price small a. If there exists a self-financed portfolio such that, okay, V0 is equal to A, I start from small a, and my final value is equal to U, so my actualized discounted final value is equal to U, okay? Or in the case of being over-replicable, respectively, Vt is greater than U. Okay. I repeat the definition. A contingent claim U at is replicable or over-replicable at price small a, notation for the price small a, okay? If there exists a self-finance portfolio or a self-finance financial strategy such that I start from small a, okay, and my final value is equal to U in the case of the replication, okay, and my final value is greater than U in the case of over-replication, okay? So in particular, it means that if I am replicable at price A, I am over-replicable at price A, okay? So what is the meaning of this one?
Can eliminate the rest.
If you want, it can be seen like this, but in other words, I said that, in fact, if you are replicable, okay, it means that you can be created by the market. What I mean by this? What is the market for me? The non-risky asset and the risky assets. It's what I am able to trade in the market. Okay, I can sell them, I can buy them, okay? It's what I have in my market. A contingent claim that is replicable, okay, will just be something that I can artificially create using portfolios. And in my portfolios, I have what? I have only quantities of non-risky assets and quantity of risky assets. Okay? And I can do this in a self-financed way. It means that once I give you the small a at the beginning, you can buy and sell in a self-financed way in the market in order to obtain, in any case at the end, capital U. Okay? So this is a strong relation here because it's a relation between random variables, or if you want, a relation between vectors, meaning that all the coordinates has to be equal. Okay? It means that in each possible state of the world, I want them to be equal. Okay? So some asset will be replicable, some asset won't be. Okay? I just introduced this definition. So here, it's the perfect replication with an equality. Okay? Over replication means that I can be greater than my contingent claim, okay, using self-financed portfolio made of the non-risky and the risky asset. Okay? And of course, in what we are going to do after, okay, it will be a way with this kind of strategy to, as you say, to eliminate the risk that is inherent to the fact that when you sell such a product, you have to be careful. Because you may have variations of the assets that will make you have to pay at the end, okay, a possible huge amount of money. Okay. Questions? So, a priori for the moment, okay, something that is related to payoffs, let's say, of European type options. And I just say that among these contingent claims, some of them may be created from the market, okay, it's what we call replicable, okay, and over replicable just means that I don't have an exact perfect equality, but I have an inequality, okay. So we are going to be interested in this kind of assets. So I introduced functional notations here. And I said that we denote by C of A, excuse me, calligraphic K of A, respectively C of A. We denote by K the set of such contingent claims. I just introduced notation. So this is the set of the contingent claim that will be replicable at price A. This is the set of the contingent claims that will be over replicable at price small a. From what we have done previously, I can be a little bit more explicit concerning these definitions. What is to be replicable at price A? It means that I am the final value of a self-financed financial strategy starting from small a. Okay? It's the definition of being replicable. I am the final value of a self-financed financial strategy starting from small a. So in other words, I can define the set of the replicable contingent claim in this way. It's the set of the things that may be written as A plus H S capital T, such that H belongs to this set where HD is the set of the RD valued and adapted, okay, stochastic processes. Why I have this? It's a consequence of what we have proved before the break. We have seen together that when I have a self-financed financial strategy, okay, so now self-financed is equivalent to the fact, it's something we have proved together, that Vt is equal to V0 plus HST. Okay, that's what we have proved before the break. So if I am self-financed, okay, V capital T will be my initial condition plus HS capital T. In this situation, my initial condition is small a. So here, you have the set of all the possible values, okay, all the possible final values of self-financed financial strategy starting from small a. So you have exactly by definition the set of the replicable contingent claims here. The one that can be written as final values of self-financed financial strategy starting from small a. Is it clear for everybody, this? Yeah? Okay. And here, in my, what I have proved previously, here you have the vector, the stochastic process related to the composition of my portfolio in terms of risky assets. That's why I have something that is adapted and with value, okay, in R to the power D, because I have D components that are the quantities of risky assets I have in my portfolio. So this is the, let's say, the functional definition of the set of the contingent claims that are replicable at price small a. Okay? For this one, okay, it will be the set of the U, okay, belonging to L0 omega Fp. It just means that I have something that is F capital T measurable. And if I want to be over replicable, it means that I have to be greater or less, excuse me, I have to be less than the final value of a self-financed financial strategy starting from small a. Here, I have the set of all possible final values of self-financed strategy starting from small a, so I can write it this way. The set of the contingent claim that are over replicable is just the set of the contingent claim written in the actualized way, such that there exists J belonging to K of A with J greater than U. I have this. So I repeat that what I have written here is just to express what I have defined in the definition 5, okay, using the notation I have previously introduced. This means that I am if I am inside, I am a contingent claim because I am equal to something like this, that is the final value of a self-financed strategy starting from small a. And if I am in this situation, U is less than something that is what? An element of here that is the final value of a self-financed strategy starting from small a. So I have exactly what I have written. Exactly what I have. Is it clear or not? Okay? No? Don't mind? It's better with the open window, I think. It's less hot. It's not the same time also. But I think that for the next session, it will be better to try to open the door and try to open the window. Yeah?
You're not defining HD clearly?
Yeah, this one. The set of the RD valued and adapted stochastic processes.
The process of HS?
No, HD. Here. You have inside what? Okay. You have inside what? You have inside stochastic processes. So H belongs to HD. So it means that you have HT that is something of this form. Okay, with value in R to the power D, D component, and something such that HT is FT measurable. So it's exactly what I have written here. Is the set of the stochastic process with values in R to the power D that are adapted to my information filtration. And from a financial point of view, it represents, okay, what are the quantities of risky asset I have in my portfolio at any time.
So H is the vector?
Yeah. Yeah, because you have something here, it's a vector here. It's a vector you have here.
No, the vector H1T to HD is H, right?
Yeah. Something with value in R to the power D. That is, okay, something that is a vector with D components.
So H calligraphic D is a sigma algebra?
No. I define where this one is the set of the RD valued stochastic processes that are adapted. It's a definition if you want this. I denote by HD the set of the RD valued stochastic processes that are adapted. That is exactly the set of the element of this form here. What is not clear? I don't understand why it's not clear for you.
You say H, then you say HT, so I'm not sure which one.
Here,
H.
it's an element of this set. What is this set? The set of the stochastic processes that are adapted and with values in R to the power D. So I said that an element of this space may be described this way. Okay? You have a set containing stochastic processes, and H here is one among these stochastic processes, an element of this space. Okay? So are you okay with this one and the one? The fact that here you have the set of contingent claims that are replicable at price small a, and here you have the set of the contingent claims that are over-replicable at price small a. Is one included in the other here?
Yes.
Yeah? Which one?
The A is in CA.
It's exactly what I have said previously. If you are replicable, of course you are over-replicable. So K of A is included in C of A. If I have the equality, I will have the inequality for sure. Okay. Remark concerning this definition. First, the notation. In order to simplify the notation, we write from now on C for C0. Okay, so I have C0 that is the same with small a equal to 0, K0 the same with small a equal to 0. I give them particular notation, that is C is equal to C0 and K, I use this notation for K0. So here I have the set of the contingent claim that are replicable at price 0, and C is the set of the contingent claims that are over replicable at price 0. Okay? So I just take A equal to 0 in both definitions here, and I denote them by C and K. Okay? Just notation. I say the following. K is a vector space. And what can you say about a vector space in finite dimension from a topological point of view? A vector space. Topological property fulfilled by a vector space. No? Nobody?
Can be divided. Divided?
Divided? What is the meaning of being divided for a vector space?
Non, le vecteur dedans.
Divisible? Ça veut dire quoi divisible? Non, non. If I have a vector space of finite dimension, on this space all the norms are equivalent. Okay, I agree, but it's not really what I ask. It's not very far, but not really. Do you have, okay, a topological property for a vector space in finite dimension? With what you say, it will mean that, okay, independently of the norm I choose, okay, I will have the same topological properties. I agree with this. So what are they? Some of them. No?
Is it a closed space?
Is?
Is it a closed space?
What?
Closed.
Yeah, closed. Yes, I am closed. So closed in finite dimension. And why I am closed? Because, okay, I am in finite dimension, so I have a basis that is, okay, a basis with a finite number of elements. So it means that any element in my vector space may be decomposed, okay, using the vector of the basis, and I can see that this condition is a closed one, very basically. Okay? So I am closed because I am a vector space, okay, and something that is more classical for a vector space. I am also convex. Okay? I am also convex because I know that a vector space is stable by linear combination. So at the very least, it is convex. As convex is something that is included in being stable by linear combination. Okay? So all the vector spaces are convex. Okay? And if you are in finite dimension, they are closed. Okay, so if I am a vector space, I fulfill this condition. This one every time for a vector space. This one because I am in finite dimension. Okay? Other question, why I am a vector space? Why this definition, okay, for k, for small a equal to 0, give me a vector space. So I remind you that k is equal to the set of something like this, h s capital T, because small a is equal to 0, such that h belongs to the set of the stochastic processes that are adapted to the filtration and with values in R to the power d. Why I am a vector space if I am written this way? So I can come back to the definition. I can prove that, okay, I am stable by linear combination. It's the definition. It's possible to prove, okay, but I have a clever way in order to prove this, okay, just by the form it takes, in fact. If I consider the mapping phi, that is from the space HD into R that associates to an element of HD the discrete stochastic integral at time capital T. But what I have, in fact, I have that K is equal to phi of HD. And what I know about phi and what I know about HD, of course,
Phi is continuous.
continuous. Yes, but why continuous? I agree with you, it is continuous. But it's not what I want to hear. Because, okay, intuitively, I have vector space, okay? And what are the mappings that are able to transport correctly the vector spaces? Continuity is not the good criteria. Continuity is in order to transform, okay, a sequence that is convergent into a sequence that is convergent. That is something that preserves, okay, the topology, let's say. If I want to preserve the fact that I am a vector space, it's linearity that is important. And in finite dimension, linear implies continuous. But here what I want to listen is phi is linear. HD is of course a vector space. So we know that the linear image of a vector space is a vector space. So that's why K is a vector space. One way to prove, okay, the short way, because it is the image of a vector space by a linear mapping. Yeah.
Root R.
Yeah. Oh yes,
Excuse me.
no. Right. It's not R, so I can write several things. I can write R to the power the number of elements in omega. Okay, but I can also write this L0 omega F capital T. I have a random variable here that is F capital T measurable, and we have said together that I can represent it by a vector, in fact. Because F capital T being the power set, I have no real measurability condition, in fact. So all the mappings works. The right thing. So I am a vector space because I can be written as the linear image of something that is a vector space. One consequence of being a vector space is that I am closed because I am in finite dimension and convex. And you will see that it will play, okay, an important role in the next session. Little question. K is a vector space. What can you say about Ka? So I am no more a vector space because you do the translation, so you see that K of A is equal to A plus K. If this one is a vector space, it's not possible for this one to be. But it's the translation of a vector space. It's what we call an affine space. The translation of a vector space by a vector. So K is a vector space, okay, as the linear image of something that is a vector space, and so is closed and convex. Okay? It's what happened for K here. For C. So C is no more a vector space, but I can say the following. I can say that C is convex and contains the following. So I just use the same notation than the one my notes. And contains what? L minus 0 of omega Fp, that is just by the set of the random variables that are negative, in fact. So C is convex and contain the random variables that are negative. It means that I have a lot of elements, okay, in the set of the over-replicable contingent claim, because I contain in particular, okay, the random variables that are negative. So why I have this? For convex, once again, it's not complicated to prove, because here you have a condition that is in fact stable if you take convex combination. If you take convex combination of elements, so you take U1 and U2, you take lambda that belongs to the interval 0, 1, you have a look on lambda U1 plus 1 minus lambda U2. It's very easy to prove that if U1 is replicable, over-replicable, and U2 over-replicable, the convex combination will be over-replicable at the same price. Why I contain the set of the random variables that are negative? Have a look on the definition. Why a random variable, so why a U that is negative belongs to this set here? For A equal to 0. Why? Because what can I take for J if U is negative? 0. Yeah. So if I take small a equal to 0 here, a negative random variable will be in C, because for J I will just have to take 0. 0 that is an element of K, because K is a vector space. So 0 is inside. Okay. So C is convex and contains, let's say, the negative random variables. Okay. And what will be important for us among these topological properties will be the fact that I am closed and convex here. Because I don't know if you remind, but concerning closed and convex set in finite dimension, typically you have what we call separation theorem. Okay, I will come back on this point in the next session, but good topological properties in order to separate space. Okay, so I have defined what are contingent claims, I have defined what are over-replicable contingent claims, I have introduced the functional analogus of these definitions, okay, and focus on what happened for small a equal to 0, and deduce when small a is equal to 0 some topological properties for these spaces. Yeah?
Well, the definition for a contingent claim is that it's an FT measurable random variable.
Hmm?
But can I ask you something? In HST, is it not measurable too?
Yeah? HST is a contingent claim. It's a random variable that is F capital T measurable. HST, capital T is what? Is the sum from k equal to 0 to t minus 1 of a scalar product here, and you have inside only things that are F capital T measurable.
What did you write just below A plus K? Affine space?
Affine space, yes. What is an affine space? Just the translation of a vector space by a vector. Okay? That's exactly what you have here. You have a vector space here, okay? By what I have done previously, I just translate it by a constant, okay, a vector here. So it's no more a vector space, but something that is just a translation. In dimension 1, you have line. okay, passing from 0, that are vector space in dimension 1. If you translate, you obtain affine lines. Okay, so it's the same, but in a dimension higher, possibly higher than 1. Okay, questions concerning what I have written on these boards or not? If it's okay, I erase everything. Okay, and we are going to continue because my aim here is to make the link between what I have defined now, okay, and the notion of arbitrage opportunities. Okay, that will be one of the main financial notion of this course. So do you have questions with the definition I have introduced here and the notations, or it's okay? Okay? So I erase. And of course I repeat, but from for the next session, okay, of course you have to study what we have done. Because we are going to start the proofs in the next session. And of course I will use all my notations. If you don't know the notations, okay, stay at home, it's better. Okay? Or have a look on the video, but once you will have, okay, a look on this session. Okay, so I erased everything. A little definition. In fact, in good financial markets, I don't want arbitrage opportunities. It's what we are going to define in this definition. Okay, I said that the no arbitrage hypothesis and I will denote NA for no arbitrage, okay? Hereafter. So the no arbitrage hypothesis is fulfilled if there is no arbitrage opportunity. Okay? I just give a name to the fact that I don't have arbitrage opportunity. Okay, I just call it NA, no arbitrage. Okay? So I remind you the definition of an arbitrage opportunity. So an arbitrage opportunity is something that is self-financed. You don't have to forget this. V0 is equal to 0. Vt is positive. The probability that Vt is strictly positive is strictly positive. So I have an arbitrage opportunity. So why I remind this? Because if I want you to prove NA, so to prove that I have no arbitrage opportunities, so to prove NA, you can take the self-financed strategy with V0 equal to 0 and Vt positive, and prove that That what? So you have the definition of an arbitrage opportunity here. An arbitrage opportunity is something that is self-financed, starting from zero, always positive at the end, with the probability to be strictly positive. That is strictly positive. So I said that if I want you to prove NA,
Yeah, we can prove that the probability that it's strictly positive is 0.
yeah. So you can prove that, in other words, okay, you can prove that, in fact,
Cannot be
VT
positive.
0. Always. This is the way to prove that NA is fulfilled. By you take something that fulfilled the tree first, and you prove that it's not possible to have the last. And what is the contrary of this one? The fact that I am 0, because I know that I am positive. Okay? So in order to prove that NA is fulfilled, you just have to prove that for any financial strategy that are self-financed starting from 0 and positive, they have in fact a final value that is equal to 0. Okay? Final value equal to 0. Okay? So it's important to have this in mind, because if I have this in mind, I have this natural way to express what is the NA condition. I said that NA is fulfilled if and only if, and that's why I have introduced the preceding spaces, in fact. K intersected with L0 plus of F omega F capital Tp is in fact reduced to 0. K intersected with L0 plus is equal to 0. Here previously I have defined L0 minus as the set of the random variables that are negative. L0 plus is just the set of the random variables that are positive. Okay? Why I have this? I have done the job already. Why I have this? Keep in mind what is calligraphic K. Calligraphic K is the set of the final value of self-finance strategy starting from 0. So you have in fact something of the type V capital T with V0 equal to 0. What is the meaning of this one? It means exactly that if I have something that is related to a self-finance strategy such that I start from 0 and my final value is positive. So here, self-finance starting from 0, final value of something that is self-finance and start from 0. This condition, Vt positive, equal to what? To 0. I don't have the choice. So the no arbitrage condition may be expressed saying that calligraphic K intersected with L0 plus is reduced to the singleton 0. Okay? And I repeat that I don't have to prove anything if you have understood what happened here. To be self-financed starting from 0, okay, is included in this one. Here I have the set of the final values of self-finance strategy starting from 0. If I impose this final value to be positive, that is this one, then it is 0. This is the NA condition. Okay? Okay or not? Do you agree? It's just a functional interpretation of what I have written here. Okay, of course, you have to keep in mind what is K. Here it's the set of positive random variables. If I am positive and the final value of something that is self-finite and that starts from 0, if NA is fulfilled, I have to be equal to 0. So for this one, it's okay, and the argument is what I have written here. Second part of the lemma. So NA is equivalent to this one. That is also equivalent to the same thing with, in fact, C instead of K. But here, it's not reduced to 0, it's equal to the empty set. This one. Not close to 0, but equal to the empty set. So for this one, I have nothing to prove. For this one, okay, I have to work. Well, not that much, but a little. And in fact, what I have to prove is that K intersected with L0 plus equal to 0 is equivalent to C intersecting with L0 plus equal to the empty set. C'est quoi?
No.
What is L0? L0 is the set of the random variables. L0 plus is the set of the random variables that are positive. L0 minus the set of random variables that are negative.
Didn't we say that K is contained in C?
So, yes, one of the part of the job, okay, will be given by the fact that we have said previously that if I am replicable, I am over-replicable. So since calligraphic K is included in C, of course, I have this inclusion from what I have said previously. If I take the intersection with L0 plus, I have this one. Okay? And of course, yes, so if I am replicable, I am over-replicable, so I have this, okay? So what I have with this one, which side I prove with this inclusion here? I have K that is included in C, okay. confused here. So K, just have a look on my notations to be clear, okay? So K is the set of the contingent claims that are replicable at price 0. Okay, C is the set of the contingent claims that are over-replicable at price 0. Okay. Ah, excuse me. No, I have, yes. That was my confusion here. It's 0. This one can't be empty because 0 belongs to C and 0 belongs to L0 plus. Okay? So it was my confusion here. 0. So since I have this, I said that which implication is obvious? This one. Because if the second one, this one, is 0, this one is included in 0, 0 being a member of this one, so this one is reduced to 0. Okay? So since calligraphic K is included in C, this implication is obvious because if I suppose this one is 0, so this one is included in 0 and in fact equal to 0 because 0 belongs to. Okay? So I have this. Because K in the L0 plus including 0 implies K enter L0 plus equal to 0. For the other side, well, let's do it by contraposition. Okay, so I want to prove this implication so that A implies B. So we are going to prove that no B implies no A. Okay? So by contraposition. So suppose that this is not true, meaning that there exists in this set someone that is not 0. So by contraposition it means that suppose that if there exists U belonging to C intersected with L0 plus, U being different from 0. Okay? I suppose that I have this. I want to prove A implies B. It's equivalent to prove that no B implies no A. So I suppose that I have no B, meaning that this one is not reduced to 0. So I have an element that is not 0 in the intersection. Okay? And we are going to see that in this case I have an element that is not 0 in the first. So what is the meaning of being in C? It means that I am over-replicable at price 0. Okay, so U belonging to C, there exists, let's say, K belonging to calligraphic K, such that K is greater than U, because I am over-replicable. So I am less than the final value of a self-finance strategy starting from 0. So there exists a K belonging to calligraphic K that is greater than U. Here. And it's finished. Why? But K is greater than U. So I have that. So K belongs to calligraphic K and L0 plus because U is positive. Okay? And what is more, K is different from 0 because U is different from 0. Okay? And so I have proved that if I have an element that is not 0 in the intersection here, I will have an element that is not 0 in this intersection. So I have proved my implication by contraposition. So this one is equivalent to this one. I can write the no arbitrage hypothesis, okay, in a functional way as K intersected with L0 plus reduced to the singleton 0, or C intersected with L0 plus reduced to the singleton 0. And in the next session, you will see that in order to handle this hypothesis and to describe it in a better way, we are going to use this characterization. This characterization will be the one that allows to make the link between the NA hypothesis, that is something that is a purely financial hypothesis, with something that will come from the theory of probability. That will be related with probability, martingales, and so on. Okay? So I have this one. Right? Questions?
Sorry, but I feel that the inclusion proves the other way.
E?
I feel like the inclusion proves the other way of the implication.
Well, maybe. In which way?
Because
If you, so let's say that I want to do basically the reasoning I have done here. I have this one. If I suppose that this one is 0, I have just 0 included in this one. Of course, I know that 0 is inside, and you have to prove the converse. That this one is included in 0, and I don't have it a priori. 0 belongs to this one. It's obvious, in fact. So from this inclusion, a priori, you can't deduce directly that you have this. Okay? On the other side, you have here, this one is 0. So this one included in 0 implies equal to 0, but 0 included in this one doesn't imply this one equal to 0. Okay? Okay, so I repeat that the lemma 3 will be the beginning, okay, of the next chapter that will be what we call the fundamental theorem of asset pricing, that is, make the relation between the NA hypothesis, that there are no arbitrage opportunities, okay, and some statement coming from the theory of probabilities and linked with the notion of martingales and so on. Okay? So it remains 5 minutes. What can I do in 5 minutes? I can maybe just introduce a definition, a lemma that I will prove next session. Okay? May I erase? I erase. So as you can see, the notion of arbitrage opportunity is a notion that is, let's say, global. And what I mean by global, it means that it's something that is between 0, that is the initial date, and capital T. Okay? So it lies between 0 and capital T. So it's something that is expressed using the beginning of a process and the end of the process. We are going to define the notion of arbitrage that is local, in the sense that it will be between two consecutive dates. Okay? So it's the notion of local arbitrage. So definition 7. So let T belongings to 1 capital T, a local T arbitrage is a ft-1 measurable random variable that I denote by xi, okay, with values in R D such that I want two things, okay, I want that C st, excuse me, minus st minus 1 is positive, and that the probability that xi st minus 1 is strictly positive is strictly positive. So it's what we call a local T arbitrage. So why this notion, and what is its link with the notion of arbitrage opportunity? So let T belonging to one capital T, a local T arbitrage is a ft minus 1 measurable random variable C with values in R to the power D such that this scalar product is positive always and strictly positive with a proba that is strictly positive. So just a remark concerning this definition in relation with what we have said previously. So what is an arbitrage opportunity? I remind you that an arbitrage opportunity is something such that V0 is equal to 0, Vt is positive, and the probability that Vt is strictly positive is strictly positive. And what is more, I have an expression for V capital T, because if I am an arbitrage opportunity, I am self-financed. So I can express my final value as the sum from k equal to 0 to t minus 1, hk sk plus 1 minus sk. And in fact, you see that in the definition of my value, because I am self-financed, I have this kind of terms for k equal to 0 to t minus 1, okay? And here, such a term is just an element of this form, because here what I have something that is fk measurable, and here I have sk plus 1 minus sk. So if you want, I can write it in the following way. It's the sum from k, so I can write it this way, hk minus 1, sk minus sk minus 1, and it's assumed from k equal to 1 to capital T. So such a term, okay, is exactly what I have here. So here, an arbitrage opportunity is something that you will do between 0 and capital T. The notion of a local arbitrage will be something between t minus 1 and t. Okay? The strategy just between t minus 1 and t during only one period of time, while an arbitrage is between 0 and capital T, that is along the capital T plus 1 periods of my model. Okay? So you see the link? These terms here in the sum are exactly the terms involved in my definition of a local arbitrage. And what is interesting between these two notions, in fact, we have a link between the two. We have the following lemma that tell me, so let T, okay, local T arbitrage is this one, it's lemma 4, that tell me that NA is fulfilled. So such strategies doesn't exist if and only if for all t belonging to one t there is no local t arbitrage. So it's something that is really useful in practice here. What is the intuitive meaning of this result that I will prove, okay, next session? So in general, okay, we work with models that are multi-periodic models. If you want to prove that the hypothesis NA is fulfilled, a priori, you have to take this one, okay, and prove that it's not possible to have such a strategy, okay? That is, you are going to work between 0 and capital T, because what I have in this definition, it's the initial and the final value. The meaning of this lemma tell you that, in fact, the notion of arbitrage, even if we think it as global, is in fact something that is more local than we may expect. That is, in a multi-periodic model, in order to prove that I have no arbitrage on the full period, it is sufficient for me to study what happened between two consecutive dates. And typically, and I will finish by this today, if you keep in mind the little model with the binomial tree we have seen together, something like this. Okay, so you have the model t equal to 0, t equal to 1, t equal to 2, t equal to 3. In fact, I see that this mechanism here may be related to sub-little markets, okay, of size 1. You know what I mean? Up, down, up, down, up, down, okay? So I have, in fact, in this situation, 6 markets of size 1 in order to have my market, okay, for capital T equal to 3. And the meaning of this lemma means that if you want to study the presence of not of arbitrage in this case, it will be sufficient for you to focus on the little markets and something that is very basic. Okay? So you can pass from the global to the local in terms of arbitrage using this property that I will prove next week. Okay? So next week the course will be from a priori 3:30, only half an hour and a half. Okay?